Well, so as Natasha just mentioned, for the past, I think, 5 years now, I've been working on voicing. It was the topic of my dissertation. Also, my postdoc is all about voicing. She did not actually mention, but the plan was for me to stop working on voicing when I got here and to work on something else to, broaden my research, kind of the area of research expertise, basically improve my chances of getting a job. So I decided to work on nasality. The lab, as Natasha mentioned, we have this airflow equipment. I'll talk about it today. I'll show you pictures of how it looks like. So I started working on nasality, and then I figured out, I actually found this really robust and largely overlooked relationship between nasality and voicing. So I went back to working on voicing. And now that I have a tenure-track job, I can probably continue working on voicing for the rest of my life. I would be really happy to do that. And basically, so the purpose of today's talk is to talk about this kind of complicated relationship between phonological and phonetic voicing, and talk about the role of phonetic parameters that are not usually associated with the voiced feature, things like consent of place of articulation, nasality, but they seem to play a major role, and not just at the phonetic level, not at the level of speech production, but also at the level of speech perception. And some of the data that you'll see today, it will tell us something about the language specificity versus universality of these relationships. So the talk will proceed as follows. We'll start just with a very general introduction to the phonetics and phonology of voicing, just a reminder of what it means to be voiced. Then we'll talk about the interaction between voicing and consent of place of articulation. Here we will look at perception data from English. I'll also show you a couple of examples from Spanish. I think there is an example from Mandarin there as well. Then we'll talk about the relationship between voicing and nasality. So here we'll look at airflow data from Russian. And then we'll talk about vowel devoicing in Southern Ute. We'll discuss the complexity of phonetic devoicing. And so let's start just with a general reminder of what it means to be voiced in phonology and phonetics. Now, I'm sure you all know that as far as phonology is concerned, this traditional phonology, we usually think of voicing as this binary contrast between something that's voiced and something that's voiceless. And if we have a phonological process, we expect a complete change. So if you used to be voiced and you undergo devoicing, you become minus voiced. Now, the voiced feature is also traditionally thought to be associated with either the laryngeal or the pharyngeal node, as you see in this feature geometry tree. And it's expected to be fairly independent of things like nasality, consent of place of articulation in the phonological tier, right? There's really no reason for it, say, to interact with other features. Now, as far as phonetics goes, voicing is also often thought to be a binary opposition, but an opposition between presence and absence of a particular phonetic trait. So the classical one is, of course, vocal fold vibration, which is something we'll be talking about most today. And here, it's very simple. The vocal fold vibration is very easy to see in waveforms and spectrograms. So if we have voiced sounds, such as in this case, we see the waveform repeating at regular intervals on top of the figure there. And then at the bottom, in the spectrum, we see a low frequency energy bar, which is called the voicing bar. So if we see these things when we open up a sound file in Prat, we know that it's a voice sound. And then if there is no voicing bar, if there's no regularity in the waveform, we know that the sound is voiceless. So very simple. Now, another cue that's relevant for stops and fricatives is consonantal duration, plays a major role in English. And here, so the idea is that shorter durations are associated with voicing, and longer durations are associated with voicelessness. So same two examples. You'll notice that the b is significantly shorter than the p. You can also look at the length of the closure of the b versus the release of the b, and it's going to be, again, shorter than the closure and the release of the p. And also for stops and fricatives, there's something like preceding vowel duration, which is also a cue to voicing. And here it's the reverse of what we see for consonantal duration. So longer vowels are associated with voiced sounds, and shorter vowels are associated with voiceless sounds. Again, so this difference is really robust, and these are examples from English. Now, there are many other phonetic parameters that are relevant for stops that can signal this phonological voicing contrast, not just stops, but also other sounds. So Lisker 86, for example, came up with a list of 16 parameters that are relevant for voicing. Some of them include things like formant transition durations, the frequency of formants, spectral properties of the release burst, and others. Now, for the purposes of today's talk, this is not very relevant. What's really relevant, though, is that so we usually associate this particular set of, say, phonetic traits with a segment being voiced, and if we get the opposite kind of settings in the phonetics tier, we would classify the segment as voiceless. But as you will see shortly in the rest of the talk, voicing is actually a lot more gradient and interactive than this in phonetics. And some of these gradients and interactions, it seems to go beyond the purely phonetic level. It actually seems to be playing a role in the grammar in general. So let's start with the interaction between voicing and consonantal place of articulation. Now, it's a well-known fact in phonetics that there's an interaction between closure voicing and place in speech production, with voiced velar stops being more likely to be voiceless than voiced bilabials and then voiced coronals. So this data comes from Natasha's and Ben's corpus study of obstruents in English. And what they found in this study, and what also has been found earlier by, for example, John Ahala, is that if you measure the proportion of voicelessness in voiced oral stops, the readings, the values are going to be much lower for bilabials than for velars. Than for velars. And this happens across different speech styles, different speech rates as well. Now, and the reasons for this are actually, very well understood. It's thought that the reason why velars are more likely to be devoiced is, there's something. So the explanation is related to the physiology of the vocal tract. And basically, we know that vocal fold vibration requires continuous airflow through the larynx. Since the air is what pushes the vocal folds apart, if there is no airflow, then vocal folds stop vibrating and then voicing stops. Now, if you think about the way labial, coronal, and velar segments stops in this particular case are articulated, we know that labials and coronals have an anterior constriction, and then velars have a posterior constriction. Now, what this means is that there is a lot more space between the glottis and the constriction for the labial and coronal consonants than the velar consonants. And this, of course, means that the airflow can continue longer for labials and coronals than velars. So as a result of this, we expect to see more voicing in labials, probably like an intermediate amount of voicing in coronals, and then the least amount of voicing in velars. So this is fairly straightforward, and I think people generally agree that this is true. Now, what we don't really understand that well is why there's also an interaction between voicing and consonantal place of articulation and speech perception. And here the general finding is that if you ask, let's say, English speakers to classify English stops, in this case we're talking about unreleased stops, they are more likely to make voicing mistakes for labials than for velars. So the proportion 29% say wrong for labials, but only 18% wrong for velars. And this is kind of surprising because we know from speech production that velars are the ones that are more likely to be voiceless. So the value should be reversed, but that's not the case. So last year, Anna Lukianova and myself tried to figure out the reason for this. And Anna, she was an undergraduate research assistant in our lab last year. I think she's still an undergraduate student here at the University of Arizona. So what we proposed is that the reason why we're getting this strange interaction, kind of reverse of what we see in speech production, is that maybe closure voicing is more perceptible in velar stops because it's less expected in production for velars. So this means that if we hear some closure voicing, if we know it's a velar stop, then we are pretty sure that the segment is intended to be voiced at the phonological level. And this would mean that this phonetic, this aerodynamically motivated interaction between place and voicing that originates from speech production actually now extends to speech perception as well. So what we did is we conducted a very simple identification experiment in which participants listened to tokens ending in stops, and the stops had varying degrees of voicing in them, and then they classified them as voiced or voiceless. So did you hear pataka or badaga? So stimulus items, they were CVC sequences. They always started with VU, and then the final consonant was either a B, a D, or a G. So basically words such as VUB, VUD, and VUG. And these were produced by an English speaker. He's not here today, but you all know Mike Hammond. So if something is wrong with this data, it's Mike's fault. So this is a sample waveform that shows one of the stimulus items. So we see the initial part is the V, then we get the vowel, and then the final part is the B. Now the B here has 9 cycles of vocal fold vibration, so they're marked above the waveform. It also has no audible release at the end, because in English, if you test released consonants, then English speakers just go by consonantal duration. So closure voicing is not a very prominent cue for English. They tend to ignore it. Even with 9 pulses, if closure duration tells them it's a voiceless stop, they'll say it's voiceless. So in order to make sure that participants pay attention to this, we used unreleased stops. And the previous studies that I talked to you about, they found the effect for unreleased stops as well. And what we did in this study is we manipulated the number of these cycles. So we had 10 steps. We started removing them one cycle at a time, starting with cycle 9. Then we removed 8 and 9, then replaced it with silence, and 7 and 9, 6 and 9, 5 and 9, and so on. So we ended up with a 10-step continuum from something that's completely voiceless to something that's completely voiced. And we did the same thing for the D and the G as well. Now, the stimuli also varied in vowel length, because English uses vowel length as a cue to voicing as well. So we wanted to see how the effect, how this, the place effect varies as a function of vowel length. So we had a short vowel that lasted 140 milliseconds, and a long vowel that lasted 240 milliseconds. So these values actually come from Mike's recordings. We didn't ask them to manipulate it, so these were his average values, and we went with tokens that corresponded to his average values. So this should be representative of English in general. So this way we ended up with 60 stimulus items. We have 3 places of articulation, 2 vowel durations, and 10 steps, and 12 repetitions of each token, so 720 tokens per participant. Now, as far as presentation goes, so the first thing we did is we thought about just randomizing everything. That's what we did. We randomized everything, divided it into 6 blocks of 120 tokens, and just played it to participants. And then what we noticed after just looking at the first, the data from the first couple of participants, is that they just tend to go by vowel duration, that the voicing effect was not likely to be significant at all. So we decided to force them to pay more attention to vocal fold vibration. So we eventually added 2 more types of blocking. So the first one is when everything is just randomized and divided into an equal number of blocks. The second type of blocking, when vowel duration stays the same within a block, but then all the different 3 consecutive places of articulation, they vary randomly. And the most restrictive type of blocking is where vowel duration doesn't change, place of articulation doesn't change. The only thing that changes is the number of glottal pulses. And we expected the effect to be the most prominent with the most restrictive blocking, because then that's the only thing that differs. So if there is an effect, it should be there. Now, we actually did find an effect in other blocking as well, but okay, I'll get to it shortly. Now, so participants, 60 English speakers, 20 per blocking type. We looked at percent voice response rates. Reaction times, we also recorded reaction times, but we did not see an interaction there between voicing and place, so I'm not going to be talking about them. Now, as far as stats go, I just did ANOVAs for now, and not very happy with this because we have a factor with 10 levels, right? So, and it's, surprisingly enough, we are actually getting a significant pairwise test even with the Bonferroni correction. So there is something going on there for sure, but I'm thinking, and if you have any suggestions for me on how to reanalyze this data, how to simplify it, so please share them. So now let's look at the results. So in the figures, we are going to start with the most restrictive blocking type, so blocked by vowel duration and place. So this figure presents the data just for the short vowels, so 140 millisecond vowels. The y-axis here is the percent voice response, going from 0 to 100. The x-axis is the number of glottal pulses, so 0 completely voiceless. 9 plus basically means 9 cycles, and whatever small amplitude vibration follows the 9th cycle. So the original fully voiced closure. And I'm using 3 different colors. I hope you can see the 3 colors. So the blue one is labial, the red is coronal, and the purple is velar, probably not the best choice of colors. And what we see in the data, so when we look at the first 4 data points, we see that from 0 to 3 glottal cycles, there are some differences in the values there, but they're not statistically significant. Now, this is not surprising because even voiceless stops usually have a little bit of residual voicing from the preceding segment at the very beginning of them, and these are all post-vocalic stops, so we know on average there's like 1 or 2 cycles, so we don't expect to see the effect right away. But once we get to the 4th cycle, there is now a sharp increase in the rates of voice responses for velars. Now, the difference between velars and labials at this point is 20%. So with 4 cycles of glottal pulsing, so 4 cycles of vocal fold vibration, velars are 20% more likely to be identified as voiced than labials. There's also a slight difference with coronals, but it's not statistically significant, probably because of the number of the comparisons that I'm making there. And then you see that labials and coronals, very quickly they catch up to velars, and there are no more significant differences with 5 through 9 pulses. And there it's probably just some kind of ceiling effect that we get there. Now, results for tokens with long vowels are extremely similar. So once again, there is nothing significant from 0 to 3 cycles. We get a significant difference at 4 cycles. Again, so here it's 20% higher for velars than labials and 15% higher for velars than coronals. And in this case, the velars are different from both coronals and labials. And then the rest are, so I guess ceiling effect once again, so the rest of the differences, they are not significant. Now here are the results for the other two blocking types. Now with mixed blocking, so this is how we started, we see that there is an effect. It's there at 5 glottal pulses only, so it comes a little bit later. It's actually surprising that it even became significant. And there are no differences with long vowels, and you'll notice that speakers pretty much went by vowel duration, right? They ignored the number of glottal pulses. So even with 9 pulses, it's never above 30%. Whereas with 0 pulses, as long as it's a long vowel, you get at least 80% or more. Now the results are a lot more confusing in the case of block by vowel duration. So here participants always hear, let's say, a short vowel or always a long vowel, but consonant place of articulation changes all the time. And it seems like this exposure to variability in consonant place of articulation results in an overall increase in the rate of voice responses for velars. So it seems like when speakers are constantly reminded how labials and coronals sound like, right, we start getting this effect. But I'm not here quite sure why. So we're getting a difference at 1 pulse, and also why the difference disappears at 6, then reappears in 7 and 8. So if you have any ideas, so please let me know. And then in the case of long vowels, again, so nothing there, probably ceiling effect once again. So to summarize these findings, we see that acoustic cues that are associated with consonant place of articulation can clearly affect perception of voicing. So voicing does seem to be more perceptually salient for velar stops, for which vocal fold vibration is less expected in speech production. And this result suggests that being perceived as plus or minus voiced is actually a very complex process that involves not only taking into account the features associated with voicing, but also features associated with consonantal place. So a lot of interaction going on there. And again, there are phonetic reasons for this interaction in speech production, but it also seems to be happening in speech perception. And even though this study focused on English only, we did have some non-native speakers who showed up for the experiment, so we gave them extra credit. We still tested them. And thanks to these speakers, we can actually say something about the language universality versus specificity of this effect. Now, so this data comes from a single Spanish speaker. We actually had quite a few Spanish speakers. This is very representative. This is what they do. So you'll notice that with Spanish speaker, if it's a short vowel, we get this prominent difference between labials and velars. So velars are much higher than labials at 3 cycles. Then the difference goes away. And there are no differences with long vowels. We also did get one French speaker, one German speaker, and this is the pattern that they are showing as well. So we get differences for short vowels, just at a single kind of point, and then nothing for long vowels. Now, interestingly enough, this is representative data from a Mandarin speaker. And what we see there is that this speaker completely ignores both vowel length and vocal vibration, simply so he or she decided to classify coronals as voiced, everything else as voiceless. And this is Mandarin speakers. So they pick up on some kind of like completely unrelated feature, and then they decide, okay, I'm going to base my decisions based on this. And then we get these very unusual results. So what this suggests is that, the rest of them are completely voiceless almost all the time. So what this suggests is that the effect that we're looking at seems to be fairly general, fairly universal, but it does seem to require exposure to closure voicing in one's native language. And of course, Mandarin does not have the stops that have closure voicing in them, so that's not surprising. Any questions so far? Okay, so this was supposed to be like a short follow-up study to my dissertation. Now this is the study where I was supposed to be working on nasality. And just like in the case of consonant place of articulation, we'll see that there is a reason for an interaction between voicing and nasality that comes from human physiology, and it seems that this interaction is really prominent. And we'll also see that the interaction seems to go a little bit beyond just a purely phonetic level. Now, this time we're going to start with a very general introduction to what pre-voicing is, because we'll be looking at pre-voiced consonants. Just want to make sure everyone knows what they are. Now it's actually very simple. There are two major types of articulating word initial voiced consonants. You can have pre-voiced consonants and non-pre-voiced consonants. So if a consonant is not pre-voiced, you just get a very short release burst followed by the vowel, so you end up with a very short VOT. So it's a short lag VOT, voices stop at the phonetic level. Now, when the consonant is pre-voiced, you still get this short burst and the vowel, but this time you are actually getting closure voicing, so the voicing vocal fold vibration that happens during closure. The first type is the predominant pattern in languages such as English, Canadian, French, German. The second type is the predominant pattern in Russian, Hungarian, Spanish, Dutch. So it's not the only type, right, for English. Some English speakers do pre-voice, but it's by far the most prominent type. Now, when we look at the languages that do pre-voice, it's actually important to point out that pre-voicing is very, very common. So it's usually found in over 90% of word initial stops. In languages such as Russian, it seems to be very close to 100%. So this is acoustic data from a recent descriptive study of Russian consonants. They found a rate of 97%. You'll also notice that the mean duration is 74 milliseconds, so quite a lot of pre-voicing. And you'll also see that many durations that we see there are 100 milliseconds or even more. So it can last up to 160 milliseconds. And this raises a very important question. So how are speakers able to produce vocal fold vibration that lasts, let's say, 160 milliseconds when there's actually a phonetic problem associated with the production of pre-voicing? And here's what I'm talking about. So we have already seen these figures. We know that oral stops are articulated with an oral constriction, which results in a limited volume of space. What I didn't tell you before is that work by Catford and Ahala as well, they actually figured out that the volume of space that we see in these figures is only enough for 15 milliseconds of voicing in the case of labials, and then only 10 milliseconds of voicing in the case of velars. Now, with this volume of space, you are supposed to produce 160 milliseconds of voicing, right? So you have to do something in order to expand this space. And there are several mechanisms that speakers can use. So one of the things they can do, they can enlarge the pharyngeal cavity, so you can do it by either lowering the larynx. You can also reduce the tension in the pharyngeal wall to somehow enlarge the volume of space there. You can also try to enlarge the volume of space in the oral cavity, so you can either lower or front tongue body. You can try to decrease tongue contact area and see if that helps. And there is something else that's the focus of today's talk, is nasal release of air. Now, nasal release of air works as follows. So again, we have a prototypical stop with an oral constriction. Soft palate is up, so nasal closure, and the air is trapped. But think about articulating it with a nasal opening. So if you articulate it with a nasal opening, you still have the oral constriction, but this time you are allowing some of the air to escape through the nose, so pre-voicing can continue much longer. And this particular mechanism, it's thought to be available to all speakers. It's thought to be used by speakers. And Ahala also suggested that maybe this mechanism can even explain the phonology of some languages. So Fijian used to have voiced oral stops. Now they are pre-nasalized stops. And he says that this pre-nasalization actually came from reliance of Fijian speakers on this mechanism. So it all makes sense, right, and straightforward, except that all this comes from English, and it's usually based on 1 to 3 speakers, usually 10 or fewer stimulus words. So also the majority of studies that looked at this, they just looked at coronal stops, how do we articulate the D, and it was collected for a very different purpose. So it was usually the goal was usually trying to figure out what are humans capable of doing. People didn't really try to address the question of whether or not speakers actually use this mechanism in everyday communication. And also, so the majority of these studies is basically John Ahala doing really invasive stuff on himself, trying to figure out what it is that you can do in order to produce pre-voicing. So we still don't know how common the nasal airflow mechanism is, especially in languages other than English. And we also don't really know when exactly the nasal airflow starts. So does it start from the very beginning of articulation, which would suggest that it's part of the entire consonant, or do you only use it once your oral pressure reaches a certain maximum, and the air needs to be vented somehow, and you start nasal venting, which would suggest it's just a purely phonetic kind of reaction to higher oral pressure. So these are the questions that we'll be talking about that I am trying to address in this study that's currently in progress. Now, data collection is now complete, but I'm still in the process of analyzing data. So if you have any suggestions for me, again, they're more than welcome. So in this study, it's a large-scale study of pre-voicing word initial stops in Russian. I had 120 test items, 60 fillers. They're all monosyllabic words like a CVC or CVCC sequences, minimal and near-minimal pairs. So basically words such as pot, bot, and then say mot, not. Now the results I'll be presenting today, they're based on 32 Russian speakers. I actually tested 64 speakers, so this is probably going to be the largest airflow study ever conducted. It takes an enormous amount of time to analyze the data. The system only records a few seconds at a time. So you end up with, and you get basically in the end, you get a single file for each of the tracks. There are 4 tracks there, so you end up with thousands and thousands of files, so it's very labor intensive. But now that I'll have undergraduate research assistants of my own, I can analyze the rest of the data. So the data was collected using the SciCon system. So the system consists of a nasal mask. There's the nasal mask, the oral mask. The oral mask has a microphone in its base, so it also records the audio signal. There's also a small tube there that speakers hold in between their teeth when they speak. It's like holding a drinking straw. And that tube measures the oral air pressure behind the lips and behind the teeth as well. And you also have like a MacBook for data collection. I'm using an iPad for stimulus presentation. It makes it look also, like high tech, and people absolutely love it. Now the system captures 4 channels simultaneously. So we get the audio channel, the oral airflow channel, the oral air pressure channel that measures pressure behind the lips. And this channel only works for labial consonants and for dental consonants, because the tube does not go far enough to get a measurement for, let's say, velars or for alveolars. Now, luckily for me, Russian coronals are dental most of the time, so I actually get the reading for labials and coronals. And the final channel is the nasal airflow channel. Now, this is how the same data looks like after you low-pass filter it, and this is what we'll be seeing in the figures today. And once you filter it, you can do various measurements on them. So right now I'm just looking at peak amplitude and peak latency, basically. And the measurements are done in millivolts. There are formulas for converting them into like milliliters per something, I forgot. But for now, it's a within subject design, so I'm just sticking to millivolts for now. Now, as far as comparisons go, I'm interested in 2 things. So first of all, it's comparing the peak amplitude of different types of consonants. So voiceless stops to voice stops to nasal stops. Russian has no velar nasal, so it's not a perfectly balanced design. And then also the peak latency of the nasal peak with respect to the buildup of oral pressure. So when exactly does nasal venting start? Does it start simultaneously with the articulation of the consonant, or does it start at some later stage in articulation? And here again, we can only look at labials and dentals. Now for stats, again, I didn't know this is the easiest thing to do probably, so I went for the easiest thing. Comparing peak amplitudes and latencies. The factors concern type of articulation. I also tried concern place of articulation, not getting anything significant there, so I'm just gonna not include it for now. Now we'll start with the results from the audio channel. And as far as the audio goes, so all phonologically voiceless stops that occur, they were all produced without pre-voicing, just as you expect, right? But they get 100% pre-voiced. So all the words that they were elicited as individual single word utterances with pauses. You only can record a couple of words at a time, so very careful speech. So not surprising that they are all pre-voiced, like really well articulated. Mean duration 82 milliseconds and the range 142 to 46. So the value is the mean, and then the range is very similar to what we saw in that other study, in the descriptive study of voicing in Russian. And then the man 100% voice. So again, just as expected. So now let's look at the airflow results. They are the interesting results. Now, as far as the voiceless stops go, right? When we look at the data from the nasal channel, and if we think about the red, the vertical line there as the beginning of the vowel, we would expect to see no nasal flow before the vowel, and also Russian vowels are oral as well, so no nasal flow during the vowel itself. So we expect to see a fairly flat line there. And this is actually exactly what we get. This was the prediction. This is the actual line. So no nasal flow. At the individual level, it's 100% of tokens. So never nasality, just as expected. So this is a very nice control condition there. Now, but when you think about the b, d, g, there are actually 2 possibilities here. If Russian speakers do not rely on nasal airflow, if they use some other mechanism, then the results should be not different from the PTK data. But if they do use nasal airflow, then we expect to see some kind of peak there before the beginning of the vowel. We don't expect this peak to be extremely prominent because the Russian speakers are not known to be aware of the fact that they prenasalized consonants, so it seems to be filtered out in perception. So there has to be some nasality there, but not enough to actually change the classification judgment towards the nasal category. And what we actually get in the data is we see both patterns. So with 22% of tokens, there is no nasal flow, so they're articulated with some kind of other mechanism that makes pre-voicing possible. But for 78% of tokens, so this is by far the majority, we get a nasal peak there. And the nasal peak is, of course, going to be significantly higher than what we see in the PTK. And it also makes the overall difference between voiceless and voice stop significant. Now, and if we look at the individual level, so the first pattern when there is no nasal flow, it's actually found in all speakers. So all speakers, once in a while, they rely on some kind of other mechanism, so not nasal venting. But only 6 speakers out of the 32 that I analyzed so far actually rely on other mechanisms most of the time, so over 50% of the time. And there are 2 speakers who try not to use nasal venting at all. So occasionally you get nasal venting, but 90% of the tokens does not happen. Now the second pattern again, so it's also found in all speakers, but this time, so we have a total of 24 speakers who use it more than 50% of the time. That includes 12 speakers for whom it's 90% of the time. So for some speakers it's probably, well, it's not the only mechanism, but it's by far the most common mechanism. And this means that 75% of Russian speakers actually use nasal venting over 50% of the time when they articulate pre-voiced consonants. And furthermore, so when we look at the latency of the nasal peak, you remember that's the second question we were interested in, we see that in 94% of the cases, so the increase in the nasal airflow happens simultaneously with the buildup of pressure in the mouth. So this is for labials and dentals. And for 6% of the tokens, it's delayed, so it starts much closer towards the beginning of the vowel. So this does seem to be a very general mechanism that speakers rely on. It's basically associated with the articulation of pre-voiced consonants. It happens the moment you start articulating the consonant. You don't wait for the air pressure to start rising and then start nasal venting. And finally, for nasal consonants, we expect to see a very prominent flow. These are nasal consonants. They perceive the nasals. So this is the expectation. This is the actual results. And nasals are significantly higher than voiced consonants, and obviously the voiceless ones as well. So these results show that Russian speakers allow nasal airflow during the pre-voiced closures of almost 80% of word initial badaga. So nasal airflow is seen in all speakers. For 75% of speakers, it's over 50% of the time, and it almost always starts simultaneously with the buildup of oral pressure. So this indicates that this nasal release of air is a major mechanism that Russian speakers rely on. It also does not seem to be something like purely phonetic, right? It seems to be, you can think of it as phonologized, or maybe like an inherent part of the entire consonant. And in other words, so this is another example of an interaction between closure voicing and a phonetic trait that's not usually associated with phonological voicing, right? But it does have a very good phonetic reason to be associated with it, and it does seem to go beyond just speech production, beyond just a purely phonetic level, right? So it does seem to be a little bit more phonologized than that. So if there are no questions, I'll move on to the final study. So this study is a collaboration with Stacy. Yeah, Stacy is there. So if you have any questions concerning, no. And this study has very different goals because it's a descriptive acoustic study that documents a highly endangered Native American language. But just like the 2 studies that we talked about earlier, it tells us something about the complexity of voicing. That being voiced or voices is actually extremely complex. It's not as simple as like plus or minus vocal fold vibration. And this time, so we're talking about Southern Ute. It's a Native American language from the Ute Aztecan group. It's spoken in southwestern Colorado, near the Four Corners area. The language is severely endangered, as I have just mentioned, of 1,400 tribe members, but fewer than 40 fluent speakers left. And the language is also very understudied. There is very limited phonetic work other than Stacy's dissertation. And I have a picture, so you will probably recognize Stacy there. So the two ladies to the left are Southern youth speakers who took part in our study. Now we'll start with just looking at the vowel inventory of youth. There are 9 vowels. It's not clear whether or not all these vowels are phonemic, and it's not really relevant for us. What's relevant is that all these 9 vowels can be either voiced or voiceless. And we're not talking about some phonetic, purely phonetic devoicing. We are talking actually about something that seems to be phonological. So an example that I took from Stacy's dissertation is the vowel E. If the vowel is voiced, if it's pronounced as voiced, it's an objective, so it's a suffix marking an object. If you produce the same vowel as voiceless, so you can think of it as a whispered vowel, it now marks a subject. So you can get a minimal pair that differs only in the voicing of the vowel. And so devoiced vowels, they're actually quite a mystery because it's not yet known whether there is the devoicing is always underlying or whether there's some kind of phonological environment that triggers it. It's also not always clear what kind of vowel a particular voiceless vowel is. So in the dictionaries of Southern youth, you get this capital H representing an identified devoiced vowel that people don't really know what it is, but there's a voiceless vowel there. And there is also this belief that some speakers don't pronounce voiceless vowels, that they may be still, they may be there in the dictionaries, but modern day speakers have lost them. And this is what we are looking at in this study, and we are starting, with the very basics. So we are investigating how these devoiced vowels are actually pronounced. So are they deleted or are they still there? Now the data comes from 8 speakers, so this is roughly 20%, right, of the entire population of all the fluent speakers left. So the results should be quite representative. We have approximately 200 words per speaker. So some speakers could not remember some of the words, but at least 200 words per speaker, and they were listed both in isolation and in a carrier phrase. Now, since nobody really knows what kind of acoustic properties are relevant for youth, we are trying a large number of measurements. I have a Pratt script that does 20 measurements for each segment. So anything that I could think of is being measured, right? And now, so let's look at the results. Now, we haven't yet done any stats, and so far I have only extracted the data for 4 speakers. So these are preliminary results, these are descriptive results. But so the segmentation was done manually, and after looking at all this endless text grids, I think that these results are quite representative, and I think that the things that I'll show you, they are very likely to be significant. And what we are finding is actually that 67% of vowels are actually deleted. So there is no evidence of the vowel left in the waveform or the spectrogram. So here's an example. So we have 2 different words. The first one has the affricate ch followed by a voiced vowel, and then the second one has the same affricate ch but followed by a voiceless vowel. So I'll play the first example. So in the first example, so we see the closure of the ch, the release of the ch, and then the vowel is clearly there, right? It's also clearly voiced. You see the waveform, the repetition of the pattern there. There's the voicing bars of darkness at the bottom, so clearly voiced. Now the second example, the sequence of the same affricate and the same vowel, but this time the vowel is phonologically voiceless or devoiced. So we get the closure of the ch, then we get the release of the ch, and then we get the closure of the ch, which is the onset of the 4th syllable, so there is no vowel there anymore, right? At least it seems like there is no vowel there anymore. But there's actually, still evidence of the vowel being there, at least at the phonological level. And what I'm talking about is the consonantal duration. So for this speaker, the average difference in consonants followed by voiced vowels and these consonants followed by voiceless vowels is 11%. So for the remaining 3 speakers, we're talking about differences of 7 to 15%. Lengthening is always more prominent in the case of obstruents, so stops, fricatives, affricates. A little bit weaker, less prominent in the case of nasals, but I do think it's going to be significant for all different consonantal types. And what this means basically is that when the devoiced vowel itself is deleted, it's actually not gone from phonetics completely. It leaves behind a trace. There is something there that signals the presence of the devoiced vowel. Now, for the remaining 33% of the tokens, we are actually seeing a vowel there in the recording that we can separate from adjacent consonants. So here's an example. This is the word for ice cold. How many of you hear a voiceless vowel there following the initial P? But if you look at the recording, right, so the vowel is still clearly there. I mean, we get this really faint, but the formal structure is there. Pratt can actually find the formal structure. We actually get something that we don't really expect in a voiceless vowel is voicing, right? So we get voicing in the waveform, the recurring pattern. We get a voicing bar at the bottom. So 33% of voiced vowels, they are produced, and some of them are actually produced as voiced vowels. But when we compare so all these tokens, right, with this vowel to how phonologically voiced vowels are realized, we see that they are quite different. So overall, so these are the values for this particular speaker. I have the averages here as well. So on average, devoiced vowels are produced with a lower pitch rate, and some of them really have creaky voicing. So this speaker has a 20% difference. Other speakers go from 18 to 25%. Devoiced vowels are also shorter than their voiceless counterparts. So for this speaker, the average difference is 36%. For other speakers, it's 32 to 45. And devoiced vowels also have lower intensity, which means that they're not as loud as voiced unstressed vowels. And here the average differences go from 22 to 33%. So what this means is that when devoiced vowels are actually produced, they are produced as voiced, but they are very different from phonologically voiced vowels. So they have lower pitch, shorter duration, lower intensity. Now we do also see these prototypical, voiceless vowels, so the truly voiceless vowels in the recording, but they are the least common type. So I'll show you an example there. Unfortunately, I forgot to embed the sound file, but what you see here, you have the N, so followed by a voiced E in the first example, the vowel is clearly voiced, and in the second example, you have the same cornel stop, but this time it's followed by a voiceless vowel, and you'll notice that you can still see the form and structure right in the voiceless vowel. So it's a truly, this is how voiceless vowels are supposed to look like, except that there's probably only 8%, maybe even fewer, that are realized like that. The rest of them are realized either as lengthening of the consonant or as a reduced vowel. And this is what I just said. So we are getting now 3 different types of producing these devoiced vowels. The most common type is the lengthening of the consonant. The vowel itself is gone. The second common type is producing a reduced vowel, and this common type is producing this truly voiceless vowel that can be clearly separated from the adjacent consonant. Now, interestingly enough, what we see in Southern Ute is actually very similar to what has been reported for Japanese. So it seems like what we are getting in Ute is actually something very general. So this data is from Naomi's dissertation. Naomi was Natasha's grad student a few years ago, and she investigated vowel devoicing in Japanese. And here you see the exact same word. So my Japanese is non-existent, so maybe Natasha can produce it, but it can be produced either with a fully voiced vowel, as in the first example, or it can be produced with a voiceless vowel, so devoiced vowel, as in the second example. And we see that in the first example, you get a very short K followed by the vowel, but in the second example, you actually get K with a very long release, and there is no vowel there left anymore. So something very similar to what we see in Ute. And just very briefly in conclusions, so I would like to go back to that feature geometry chart that we saw at the beginning of the talk. So as you remember, according to traditional phonology, we would not expect voice to interact with the rest of the features there. So any manipulation of voicing should be independent of, let's say, nasality, consonant place of articulation. But the data that I presented today actually shows that even beyond speech production, actually in speech perception as well, you can get interaction between voicing and place. You can also get interaction between voicing and nasality. That also seems to go beyond just a purely phonetic level. And also, Southern Ute data showed us that a change from plus voiced to minus voiced doesn't necessarily mean just absence of vocal fold vibration. There can be a lot more going on there. So that's the end of the talk. Thank you very much.